In this experiment, we are going to talk about the bipolar junction transistor, and we are going to simulate its DC characteristics, see two forms of biasing. First is biasing using a voltage and biasing using a current. So we want to see the effect of these two on the output resistance and the breakdown voltages. And I'm going to explain two breakdown voltages associated with uh, a bipolar junction transistor. So let's get started. Okay, so I have here the library, which is a study library, a study PDK attached already, and it has a include file here. So if you look into the include file, uh, you can see that there is a BJT model here for HBT. Now this I am referring to BJT, but actually it's a HBT. It's a IBM SIGE 5 HP process. It's a mock-up of that. It's not exactly that, but it's a SIGE HBT, the way it is modeled. Now there is no mechanism at the top level to scale it, so only what you can do is you can add the multiplicity. Now here I'm declaring that each finger, each you can say emitter finger, is 50 micron long, right? You can change here to any number you like, but that will change in the overall design. So I'm going to design everything with a 50 micron finger. And second thing is that the width of the finger, okay, is 0.5 micron, which is fixed for this process. So one finger is 50 micron long and 0.5 micron wide. So that's what we are going to use for a model. Okay, so I'm going to cancel that. Under device characteristics folder, I have created a new schematic called HBT. HBT characteristics. It's a blank schematic. You can create any new schematic, call it HBT characteristics. Now to be able to use that device, you need to go to devices BJT, and here you have to look for a non-linear model. Okay, okay, now the difference between the two here is this model has a terminal for the ambient temperature, and then you can put a self heat on this, and it will calculate what should be the junction temperatures. Now we can use this model if we were to put an ambient temperature. While you can do this also here, while you are simulating, you can set the simulation in device ambient temperature in the simulator simulation controller itself. So I'm going to use this one. Okay, now here the model it says is BJT M1, right? So let's put here the include file. That's the include file, and let's look into the file. What am I calling the model? The model is called HBT NPN, right? So HBT capital NPN. Okay, so I will call this as HBT NPN. Okay, so that takes care of this instance referring to that model. There are other inputs which we can just leave. Okay, so here the default is on. Okay, so you can use this model in the reverse biasing, where the collector base junction is forward biased, and base emitter junction is reverse biased. That's the reverse operation. So right now we are going to put it in the on mode, and we can specify operating device temperature. Default is 25 degrees Celsius, and you can also specify the junction temperature, which is a temperature rise above ambient. So we are going to ignore all that stuff. Mode is non-linear, noise is yes. Multiplicity here I can put 50. I want to make a 300 or a 600 micron device. So a 600 micron device will require 12 fingers because each finger is 50 micron long. So so when I say 50 micron long and 0.5 micron wide, it is 25 micrometer square is the emitter area. Okay, so basically, unlike BJT and unlike FETs, where you are working in gate length, the gate widths, right? For the size of the device is the ratio of W by L, and you are working with gate widths. So you mentioned that what is the device size? You mentioned the width in millimeters. But in case of HPTs, we work in terms of emitter area, or rather we would say emitter periphery. So what is a periphery? It's a parameter. So for example, a finger is a rectangle which is 50 micron by 0.5 micron. That means that this is 25 micrometer square periphery, right? Now, if I say parameter, it would be 25 plus 25 plus zero point 0.5 plus 0.5. So that would be basically a parameter of the emitter. Now, I'm going to explain you why parameter is important rather than emitter, or emitter periphery is more important rather than the emitter junction area. Because the device is mostly under high current densities, it's only conducting on the emitter periphery rather than the entire emitter junction area. So we will talk about it, and this is a very important concept of emitter current crowding, right? Okay, so let's put here a multiplicity of, let's say, 12. So a multiplicity of 12 would mean that the emitter junction area is 25 into 12. Okay, so a 25 into 12 would be 300 micrometer square is the emitter area, 300 micrometer square. So I'm just going to display the multiplicity, the model name, and that's it. Okay, so now the devices, usually the large devices have very large gain at the lower frequencies, and they tend to be unstable. Now usually an analog designer would not worry about the termination, and he would directly go ahead and bias this device using the supplies. Now just one second, you can use F5 to move the text. Okay, now the issue is you cannot, if you are going to use for RF purposes, yeah, the device tends to be unstable and open or short. So basically, if you directly put here a supply, so for example, I can take a supply here, and I can directly put here as VCC and VBB, correct? So I can name this as VCC, and I can name this as VBB. Now the issue with this is, if I was to directly connect these supplies to the collector and the base respectively, so if I directly connect from here to here, right, so or from here to here, the problem here is that it will present short to the collector and short to the base. Now these are the two regions in a Smith chart, short and open, which tend to be unstable. So rather we would terminate this transistor for RF at the center of the Smith chart, which is most likely to be stable, right? Because the DC characteristics will not mean anything if the device is oscillating, right? Okay, so for that we have to place the termination of the transistors to 50 ohm before I do a DC characteristics. Okay, so let's quickly do it. To do it, I'm going to do a DC feed, which is like a RF choke, which I'm going to connect here and here. Sorry about that. And here I'm going to connect them like this. Okay, now I want to monitor both the currents, the base current as well as the, I want to monitor the base current as well as the collector current. Now let me just delete this. let's put here feeds, DC feed, the emitter or the probe components. Okay, I'm anticipating that the base current will flow this way for the forward active region. Call this as IB. Okay, so I'm measuring base current. Now remember, base current has two parts. One is called one is due to the recombination in the base. The other is due to the holes which are flowing from base to emitter being forward biased. Okay, so that is IB1 plus IB2 as IB. Next is I'm going to put a probe here, and I'm anticipating a current flowing this way, and I'm going to call this probe as IC, which accounts for the collector current. Okay, so now this probe is going to measure collector current, this probe is going to measure base current, and I also want to observe this node voltage, which I am going to name as VBE. And in a second I will tell you why am I doing all this, because I want to show you the characteristics of a BJT which test books cannot provide. Okay, what is the next is this is a termination of open circuit on the base as well as the collector, right? Okay, so we want to terminate it to not to open but to 50 ohm. So I'm going to use coupling a DC block over here, and then I'm going to give it a RF termination. So that would be a 50 ohm terminal. From S parameter I can get that 50 ohm termination. So notice that now the termination is 50 ohms, which is supposed to be the most stable part of the Smith chart of an unmatched BJT. Okay, so we are ready for simulation. We have used two variables, VCC and VDD, so we would have to declare them as variables. So one variable is VCC, so capital V, correct, and let it be any value. You can put here, let's say 2.2 volts. Okay, and the VBB I am going to put as 0.6 volts, which is like a turn on for a base emitter junction diode. Okay, so 0.6 volts. Okay, so both the variables are declared here. Now I want to do DC characterization, right? So I will go to simulation DC, and here I'm going to sweep VCC from 0 to 3 volts. So I'm going to sweep VCC from 0 to 3 volts, and I can choose the step size to be a small number so that you get smooth curves. Okay, so per trace it will be like 3001 points. If you want, you can also display the variable to sweep, start, stop, and step. Say OK, and that's what you are seeing here. So this is for VCC. Now I also want to sweep VBB for getting the output characteristics. So I am going to go here to parameter sweep, and in parameter sweep I'm going to sweep the variable VBB, and I am going to go from 0.5 to 0.7, 0.5 to 0.7 or 0.6, and I'm going to go steps of 0.0 0.02. Okay, so I'm going to have 6 traces. Later I can change these numbers. Simulation here is the previous sweep is in DC1, so that's why I put here DC1, and displaying is sweep variable start stop step. So I can see here I am going to do this sweep on VBB. Okay, so we are ready for simulation. Okay, and this is basically I am biasing this with a voltage source. Now I'm going to explain you what is the difference biasing with a voltage source or a current source. When you bias with a voltage source, what's going to happen is that the collector base junction is reverse biased, and as you increase the collector voltage, which is VCC, the collector base junction becomes more and more reverse biased till it breaks down. Okay, and there is a increase in the leakage current, which basically is going to flow into VBB because it acts like a sink. So the current, which is a leakage current from collector base junction, is going to flow into VBB and it's not going to go into VBE. So what it means is that the collector base junction is breaking down, and whatever is the leakage current on the breakdown is collected by VBB and doesn't go into VBE. The point of doing this is that the excess leakage current, if it goes into base emitter junction, it is going to be amplified by beta on collector on the collector current, right? And that beta being 100 110, okay, the leakage current basically amplifies the collector current by that much amount, and this causes the further enhancement of avalanche breakdown which collector base junction is going through. Okay, so we have to avoid the current, leakage current, going into base emitter junction. Rather it will be collected by the base supply. So what happens in doing so is that the base current would become negative, and the collector base junction breakdown would be at a higher voltage. Okay, so that's why if we bias it with a voltage, the breakdown voltage of the device will be much higher, because you are seeing a collector base breakdown voltage. You are not seeing a collector to emitter breakdown, or you are not seeing VCB. We are seeing VCBO, collector to base breakdown with emitter open, versus VCEO, which is collector to emitter breakdown with base open. Okay, which is when you bias with the current. So the two breakdown voltages are going to be almost, the collector to emitter breakdown with the base open would be almost half of the collector to base breakdown with emitter open. It is basically beta raised to n, where this beta is your forward current gain. So I'm going to explain this later on, but let's go ahead and do the simulation. Okay, so simulation is done. I am going to plot collector current, and you can see that these are your characteristics. Now let us extend this beyond 3. Okay, let's go up to 3.5 volts. Sorry, 3.3, or rather 3.3 is okay. Okay, you are starting to see this breakdown. Let's further increase it. 3.6. Okay, so you will see that you are going to see the breakdown. Okay, now one more thing I want to do is let's increase this to 0.65. How's that? Okay, I think let's go further up. Let's say we go up to 5 volts. How's that? Okay, now you are going to start seeing the breakdown. Okay, you are even up to 5 volts, you are going to start seeing the breakdown. Now what I'm going to see is I'm going to plot the base current. So here I can plot IB and I'll put it on the right hand side axis. Notice, now here you can notice at 3.3 volts the base current on the right hand side axis you can see becomes negative, right? Now what I told you was that 3.3 volts, the collector base junction is going through breakdown and the reverse leakage current is basically now being collected by IB, right? So that's why it shows up in that shows up as IB as a negative current, because VBB is basically collecting that current. The current is not flowing into base emitter junction, rather it is all collected by this supply. So you can see the difference. So you can see basically what's going on when the collector base junction grows into breakdown. Okay, let's put here. Okay, so let's not make it that thick. Okay, so I guess I have made my point here, that when you bias it with the voltage, then this is happening. Another thing which is happening is that as you increase VCC and keep fixed VBB, or VBE is fixed now. Okay, so let's put let's plot VBE also. VB is fixed, right? So we are sweeping these values. So basically these values are fixed and they don't change with VCC. So VBE is fixed and the collector voltage is increased. Now as the collector gets more and more reverse bias, the base width gets modulated, because you know the depletion region in the base extends more towards the emitter. So WB shrinks, and because WB shrinks, there is a output resistance here. Okay, so there is a output resistance which is inverse of this slope here. So basically if I draw a line, and this line, the inverse of this slope basically represents the output resistance. Now I can extend this, and this is going to intersect. Okay, I can keep extending this, and somewhere it will intersect the zero axis. Okay, IC equal to 0. So someplace it is going to intersect here. So let me just show you that part. So keep extending, and somewhere it is going to intersect. So books basically can show a exaggerated value, so the intersection comes in that case very early. Okay, somewhere here. Okay, so this voltage is minus VA, or it is called the early voltage, and all the curves, all the current curves for basically different IB, different VBE, sorry, they are going to, sorry, they are going to meet the same point. Okay, somehow I'm not able to grab it, but it's okay. I can draw another line. So basically all are going to intersect at the same early voltage. Okay, I hope you understand what the early voltage is. Okay, so all the current curves are going to meet at early voltage if you extend it back. Okay, so this is the cause of the output resistance. Okay, let's get rid of this now. So now you have understood why there is an output resistance. There is an output resistance because the base width gets modulated, or rather base width gets reduced as the VCB or VCC is increased, because VCC is nothing but VCB plus VBE, and VBE is fixed by VBB, so VCB is only increasing. Okay, so I hope you understood the biasing using a what you call, using the voltage source. Now I am going to turn this into a current source. Okay, so let's disable this. Okay, and I'm going to put here a current source. Sources, frequency domain, and I'm going to pull here IDC. So this is going to force a certain current in it, into the base. Now notice VBE is established by the base current now. Okay, and I'm going to call this as IBB, and let's say capital IBB, and here I am going to make it a microamperes. Okay, now here this VBB is of no consequence here because VBB is going to be established by the current. So I'm going to turn this into IBB, and I am going to go from, so if I put in 1 micron and it is 100 beta, so the output current would be 100 micron. Now if I want to be in the same range, roughly here, which it goes up to 40 microamperes, right? So 0.4 is 40 microamperes, right? Because the beta is 100. So I will go a default value of, let's say, 0.4. Apply. Okay, now here what I'm going to do is I'm going to change the data set, and I will call this as C, capital C. I'm going to put a suffix here, capital C, say apply, cancel. Okay, so now I'm going to vary IBB instead of VBB. And the value I'm going to go from is going to be 0.1 to, let's say, 0.4, right? And this one I'm going to say 0.5. Okay, so 7 curves are there, and say okay. So I have changed the data set now, and I'm going to sweep IBB, so I'm biasing it with the current rather than with the voltage. Now if I was to simulate, I think we are ready for simulation, right? So if I was to simulate this and say no, now let's plot from a different data set, which is suffix C. Let's plot the collector current. Okay, what happened wrong here. Oh, because it has gone into breakdown, that's why. Let's not sweep up to 0.5, let's sweep up to like 3.6. Okay, because in this case it is breaking down faster. So let's go up to 3.6 and simulate. Okay, so now you see where the currents are going, where the currents are going negative, there actually the breakdown occurred, right? Now these currents are picking up here. So let's even reduce this further. Let's put this as 3.4. Okay, now you are going to see the previous curve. So even 3.4 is large. 3.3, 3.2, something like that. Okay. Okay. So if you remember, the red are because of the biasing with the voltage. And this pink one, I'll make them green, is biasing with the current. Okay. You would notice that this is going to be flat, more flat. The output resistance is going to be larger, because this is because you have fixed the base current. Okay, so when you have fixed the base current and collector base junction is not in the breakdown, it is in this region, it is not gone into breakdown yet, it is breakdown beyond 2.5 volts. Okay, so beyond 2.5 volts it goes into breakdown, right? And so before that, or lower values of collector voltage, the collector base junction is not into breakdown, right? The base current is fixed by this IBB. So hence the collector current has to be beta times of IBB, and beta is basically constant. So what you see is going to be the current, collector current is going to be constant. It will be beta times of IBB, right? So this is going to be flatter. That means that the output resistance of the device when biased with current is going to be larger, right, in the forward active region. That means that if you bias it with a current source, you can get a higher gain out of these devices, right? Okay, so we will see what is the gain. Okay, uh, it will be GMRO only because it is a common emitter. So RO is large, so the gain would be large if you bias it with the current. Okay, but the breakdown voltages are going to be less. Or you can also say that the device can be more linear in the forward active region when biased with a current rather than biased with a voltage, or the gains would be higher. So I hope you understand what I'm saying. The issue is the breakdown voltage has drastically dropped. It is the collector to base breakdown with emitter open divided by nth root of beta. If nth root of beta is n is 4, roughly it will be half. So if the breakdown was to you are going to see at around 5, you are going to see the breakdown around 2.5, half of it, because now the current, the leakage current of collector base breakdown is flowing into base emitter junction rather than being absorbed by the base terminal as in the earlier case, and this causes the leakage current to be amplified by beta, and this is like a positive feedback which causes the avalanche to take place at a much lower voltage. That is why VCEO would be BCBO divided by nth root of beta, or it will be much reduced. And the base currents are going to be positive here, right? So if I was to plot here base currents, because the base current is fixed by the base supply voltage, and let's put it on the right hand side axis. Okay, let me make it dot, and let me put it on the right hand side axis. Okay, so brown. Okay, so notice that the base current, which is the brown colored curve, these are flat. These are not becoming negative because we are biasing it with a fixed current source. So that is why they are not going negative. Okay, and all the collector base leakage due to breakdown is going into base emitter junction and gets amplified by beta and then shows up in a collector current. So the avalanche is enhanced because of this positive feedback. So biasing with the current source is doing that. Now at the same time, you should also observe what is VBE when you bias it uh, with the current source, and it should follow the same IC characteristics, because once you fix the base current, which is mostly the whole current, that means that you have fixed the slope of minority carriers in the base. Okay, so when you have fixed the slope of minority carriers, then under breakdown the VBE has to shoot up. Okay, so as you keep increasing the collector current beyond 2.5 volts, the VBE is going to shoot up, resulting in avalanche breakdown. So let's see, from this, let's see VBE. So now you can see that, okay, VBE is flat because the collector base junction hasn't gone into breakdown, and the current density, the minority carrier density at the base emitter junction is fixed because of the base emitter, because of the base current, right? And that's the slope is fixed, right? And that's why the collector current is fixed. But when it goes into breakdown, VBE has to go up, right? Because your VCE, basically increase in VCC, shows up in increase in VBE, and that basically is causing the avalanche breakdown. So I hope you understand that in case of a BJT, you can bias it with a voltage and you will see higher breakdowns because the base is drawing the current in the reverse direction, avoiding the avalanche. When you bias it with current, you will see that the avalanche occurs at almost half the voltage of the breakdown when the emitter is open, right? So that's the basic difference. Now for linearity considerations, you might like to bias it with the current, but then to get the power out of the device, you want something to absorb the leakage current when collector to base goes into breakdown. So that can be done by a small circuit trick, which basically is a patent of IBM. So I can hang a smaller transistor here like this, okay, and I can fix the breakdown voltage by, this is going to be basically diode connected kind of connection, and I can put here a resistance here, and this resistance can be scaled to break this, to cause the breakdown, to avoid the breakdown, right? So I can put here a 1K resistor, for example, or 2K resistor, okay, like this. Now what is going to happen is when collector base junction breaks down and VBE goes up, now I can scale this resistor such that the net VBE here is going to turn on this device, and this runaway which you see is going to get delayed because I have turned on this device and absorbing all the collector base reverse leakage current in this device, and so it doesn't show up in VBE, and hence the avalanche basically is pushed out when you bias it with the current source. So this way you can have best of both the worlds. One is you are biasing with the current, so you are seeing higher output resistance, higher gain, and better linearity. Second is because you are putting here a beta helper kind of stuff, which is absorbing all the collector base reverse leakage current when collector base junction goes into breakdown, and hence extending the breakdown voltage to be 5 volts. So same as bias it with the voltage. So I hope I have explained the characteristics of BJT and some of the tricks related to biasing with voltage and biasing it with current. So this is the end of the experiment. You can run this simulation to learn more about BJTs, and when you design power amplifiers or low noise amplifiers, you will come to know how BJTs can be used, right, for various applications. So in this course we are going to limit to only DC characteristics. Another thing is in the class I'm going to explain you the other RF characteristics, like what is FT, FT versus IC characteristics, beta. Also we have one more experiment to plot log of beta, log of current, collector current and base current versus VCE, which is basically called Gummel plot. Okay, so first I'll explain it in the class what is a Gummel plot, and the next experiment we will plot the Gummel plot, and we will try to see if I can plot a FTIC characteristics. Okay, so I'm gonna stop here for this experiment.